I want to go back to the photoelectric effect. If you remember what that was when it's something that Einstein looked at, examined, built off Planck's idea. If you remember, Planck's idea was that energy is quantized. He came up with this Planck's constant. Oops. Sorry, I don't know what happened there. Let me just get my pen out. Okay, this is, we talked about this last time. By the way, I forgot to tell you, this is actually called Planck's equation, or it's actually also called Planck-Einstein relation. And we talked about that energy comes in packets, quanta, right? And Einstein built off that idea when he talked about the photoelectric effect. So the idea, if you remember, was that if you take light, the intensity of the light doesn't affect the energy of the electrons as they get ejected from the metal. What actually affects the movement of the electron is when you play around with the frequency. So if I make it, for example, you can see with ultraviolet light, which is a higher frequency light, I get faster moving particles. As I move to the visible light, you'll notice that I don't see any more fast moving particles. They're all slow moving particles. If I play around with the intensity, what the intensity does is it just changes the number of electrons that come out. Obviously, if it's brighter, there's more electrons coming out because there's more light. But it doesn't change their energy or their speed. Now, I want to go back to that because I don't think I did a great job of explaining that, to be honest with you. So let me go back to, because that's actually pretty contradictory result when you think about waves. Last year we did waves. So we talked about frequency was one of the wave properties. So the result, and I guess one way to think of the result that we just saw with the photoelectric effect would be, imagine that higher frequency sound has more energy than low frequency sound. That doesn't seem right. That doesn't seem at all right. But yet that's what you're seeing with light, where the energy is a function of frequency. What you should remember from last year is the energy of a wave is its amplitude. We actually did some demonstrations with that. And actually, if you remember, we actually did sound intensity calculations, which were a measurement of how loud sounds are. So the intensity of a wave is a measurement of its energy. But you can see that light is different, right? That's a very, very bizarre result if you think of it in that case as a wave. And that goes back to the idea of what is light. Obviously, it does behave like a wave, but in this case, it's not. So that comes then to the conclusion that Einstein realized that light is also a particle. It behaves also like a particle, where the energy of the light has nothing to do with the intensity of the light, but it's a function of the frequency, again, building off of Planck's idea. Okay, questions about that? Okay, so then, and when we did these calculations already last time, I believe, right? Okay, so then what we're gonna do today is we're gonna talk about, did we do this last time, momentum of a photon? I don't think we got to this, right?
No, we didn't do it yet.
Okay, all right, so then, we can talk about, even though we know that light doesn't have per se mass, we could still assign it a momentum because it has energy, okay? And I'm gonna show you kind of the derivation of this. How do we get an equation that shows that light has momentum? Well, it actually has to do with a bunch of equations that you're seeing on my screen right now, okay? You'll notice that you have, this is Planck's equation, or the Planck-Einstein relation. This is E equals mc squared. This is the equation for momentum. this is the wave equation, right? So what we can do is we can put these together to show how we can calculate the momentum of a photon, okay? Not as a function of its mass, but as a function of Planck's constant over its wavelength. So let's start with E equals hf, okay? Now, E is also equal to mc squared. So what we could say is hf equals mc squared. Now, if you look at for the equation for momentum, we could say that, well, m is also p over v. So we could write hf is p over v times c squared. But what is v? Well, v is actually c, right? Because we're talking about the speed of light. So that becomes hf equals p over c times c squared. So obviously, it'll just be hf equals p c. Okay. So now you have an equation where hf equals pc. Let's rewrite that so it's a bit clearer. But what's c? Well, c is f times wavelength, right? The wave equation. Where v equals f lambda, we can say c equals f lambda. So there you go. Now you'll have frequency on both sides, so they cancel out. So you're left with h equals p lambda, or we could rewrite that and say p equals h over lambda. There you go. There's the proof that photons have momentum. Now, what a really cool futuristic application of this is something called solar sailing. You ever heard of this? Anyone ever heard of solar sailing? None of you have heard of solar sailing? Come on. I'm sure you've heard of solar sailing.
Nope.
No? Do you know how a sailboat works? Let me draw you a sailboat. How does a sailboat work? How does a sailboat move? What does it use? It uses a sail, right? So the wind provides a force. There's obviously air moves because of differences in air pressure. So the force that air exerts on the sail, so here's my sail, causes the sailboat to move. The idea behind a solar sail is you can get ships in outer space to move if they can use a sail, but not obviously to capture air, but to capture photons of light as a way to get space travel. I guess that would be space travel that is, pretty efficient, pretty cheap, doesn't require any fuel. It's just a matter of capturing photons from stars. Kind of a cool application. What do you think of that? Isn't that cool? By the way, did any girls watch the Dragon X space launch? Apparently they launched last week. Any of you girls see that? I didn't see it. Forgot to look into it.
Yeah, I watched it live. It was really cool.
Yeah. Now is that the rocket that technically could land back on the surface of the Earth?
Oh, I don't know. I'm not sure because I think that. So you mean would it come back or not? Is that?
Yeah. I think so. I could be wrong, but I think that's supposed to be a reusable rocket. But I could be totally wrong. But if you ever looked up the videos where the rockets actually come back and they land, it looks like watching a rocket take off in reverse. It's really, really cool. I have to look into that. Yeah. Anyways, okay, cool. All right, so let's talk about the momentum of a photon. And let's do, simple calculation. So what would be the momentum of a photon that has a frequency of 1 times 10 to the 4 hertz? Sorry, 10 to the 14 hertz. Okay. Oh, sorry, the question in the chat. Can you say that, Maya? What you just messaged me? That's an interesting fact. Really, eh?
No, yeah, it was an interesting fact.
Yeah, no, that's kind of cool. Can you want to say it?
So it was like the Compton's name in the last page.
Yeah.
So like he won the Nobel Prize for the thing that he did with electrons.
Okay.
And how like the momentum of photons.
Yeah.
And he was involved in Manhattan Project. And something interesting about him is that with his 2 brothers,
Yeah.
they are the first trio brothers that earned their PhDs from Princeton.
Wow. So 3 brothers went to Princeton and earned their PhD there, right? That is so cool.
Yeah,
that
and then
is so cool.
One of them won the Nobel Prize. One of them became the president of MIT, and I don't know what happened to the third one.
That's really cool. Thanks for sharing that. That's awesome. All right, let's get the momentum of this photon. It has a frequency of 1 times 10 to the 14 hertz. So we know the equation for momentum is whoa, what happened there? It just disappeared on me. Wow, what just happened? Sorry, it just disappeared. Let's call that up again. Sorry about that. I don't know what happened there. You can hear Kristen saying it's the Lenovo. You can already hear that. Okay, so where were we? We're looking at the momentum of this photon of light. Okay, so we know P equals H over lambda. In this case, you have the frequency. So we know that V equals F lambda. So I guess what we could say is P equals H over, well, if we rearrange for lambda, it's V over F. So that means H times F over V would also give us the momentum of this photon, where V is obviously C. So that would give us Planck's constant times the frequency, that's 10 to the 14, over the speed of light. And obviously, if this is momentum, we should know the unit is going to be kilogram meter per second, okay? So that's going to give us a momentum of, I did the calculation right to save some time, about 2.2 times 10 to the minus 26 kilogram meter per second. So obviously, you're not going to notice that. That's such a tiny number that if someone were to shine a flashlight on you, nothing would happen, right? You wouldn't even notice that. Okay. All right. Questions about how to calculate momentum of a photon? What's really cool is you can see then that, like thinking going back to light, that, light is a wave, but it can also behave like a particle. And I think we talked about this last year, something like an electron. We think of the electron as a particle, but quantum mechanics says we need to also think of it as a wave. And I think we talked a little bit about that last year when we talked about, I think we did it in chem. Girls, refresh my memory. Did we talk about how the electron can also function as a wave? Remember we talked about when you fire electrons to a double slit, you get an interference pattern. Do you guys remember that? Or am I thinking incorrectly here?
I remember it.
Yeah? Okay. So that experiment showed that when you put electrons through a double slit experiment, it produces an interference pattern, just like waves would. So wave particle duality means that you can think of something as both a particle and a wave. And we can think of even like an elephant as that, because de Broglie suggested that anything that has momentum would also have a wavelength. In other words, if we take the momentum equation that we just looked at, we could rearrange it to find the wavelength of any object. Hold on, something in the chat here. Oh, is it minus 28? Yeah, I can't even read my own writing. Thanks, Kristen. You're absolutely right. This is minus 28, not minus 26. Thank you. What would I do without you girls? Yeah, it's minus 28. Thanks, Kristen. Is that Kristen? Very nice, Kristen. Yeah, perfect. Thank you so much. Okay, so we can rearrange that equation, the equation for momentum of a photon, to figure out the wavelength of anything. Anything with momentum would also have an associated wavelength. And something like a cannonball traveling at 100 meters a second with a mass of 5 kilograms would have an associated wavelength. Now, why don't you notice the cannonball behaving like a wave? Okay, here's why. If we plug the cannonball into this equation, right, which is just simply the equation, momentum of a photon equation rearranged, then we get a wavelength that you'll see why we don't notice a cannonball behaving like a wave and why it behaves like a rock or a particle, okay? So it's Planck's constant over mv. So the mass is 5, the speed is 100, okay? That would give us an associated wavelength of 1.33 times 10 to the minus 36 meters. Now, when we see a cannonball flying through the air, it behaves like a particle. It doesn't behave like a wave. It's because the wavelength is so small. In fact, I put up a little chart here. You know, if you look at the smallest possible wavelengths for electromagnetic radiation, you're looking at gamma rays. So that's 10 to the minus 14. This is 10 to the 22 times smaller than that. So obviously, this associated wavelength is so tiny that we don't even notice it as if it was behaving like a wave. However, when we look at the next thing, which is an electron, you'll see something a little bit different, okay? Because remember, electrons, we can think of it as a particle, but it also can behave like a wave. And you'll see why when we do this calculation, okay? We do the same thing with the electron. Well, first, before we do that, we need the velocity of this electron, right? So what we could do from chapter on electric fields is we could figure out the speed of this electron. We could say that the kinetic energy of my electron would equal the charge of the electron times the voltage. We could rearrange, to figure out what the speed of my electron is. So I already did the calculation. It should be 6.5 times 10 to the 6 meters per second. But based on what happened last time, maybe I should have double checked, right, Kristen? What do you think? Should I double check this? So it's, let me see. So it's 2 times the charge of the electron, which is 1.6 to the exponent negative 19, times the voltage, which is 120 volts. It is 120 volts, right? Let me just double check. Yep, 120 volts. What happened? Where's my okay? Equals this divided by the mass of the electron. We'll give it this number. Take the square root of that. So yeah, 6.5 times 10 to the 6. That's good. Let's double check. Okay, got it. So that's correct. So 6.5 times 10 to the 6 meters per second. Okay. Now, if we plug that in to the wavelength equation, I call it the wavelength equation. The momentum equation rearranged, we get h over mv. So that's going to give us 6.63 times 10 to the minus 34 over the mass of the electron times the speed of the electron. And that's going to give us a wavelength of approximately 1.1 times 10 to the minus 10 meters. So in other words, that would be a wavelength that would, be somewhat in between. It looks like it would be X-rays if 10 to the minus 8 is UV and up to 10 to the minus 12 X-ray. So it would be in the wavelength of the X-ray range. So it would behave like a wave also, right? Because its associated wavelength is within that electromagnetic radiation wavelength range, specifically in the X-ray range. Okay, questions about that? Okay, all right, so then let's move on. We can, and they're all connected here. They're all talking about, all these equations are using Planck's constant to determine things like wavelength, energy of photons, stuff like that. So we're going to continue with this idea and talk about absorption and emission spectrum. And I think you're introduced to this idea maybe even as early as grade 9 when you do this with analyzing stars. Talk about probably the emission and absorption spectrum to figure out what's in the star. Did you guys do this in grade 9? Talk about emission absorption spectrum? You definitely do it in grade 11 and probably in grade 12, right? What we can do is we could talk about this and be able to predict what colors of light get emitted after photons are absorbed. Okay. Now remember we talked about the symmetry between absorption and emission. Absorption is when a photon of light, the energy is captured by an electron and jumps to a higher level. And then as it jumps back down or falls back down, it releases, assuming it falls back down exact same amount, it releases the exact same amount of energy. So for example, if this is my nucleus and this is, ground state, if an electron jumps up a level by capturing a certain amount of energy, it's going to release the exact same amount of energy when it comes back down to the ground state. Here we have an example. We're talking about, for instance, mercury. And if an electron is on the ground state, it requires a certain amount of energy to get to the second level, or the first level above the ground state. It says it requires about 4.9 electron volts to jump. And it can go to the third level or the second level above the ground state if it captures 6.7 electron volts of energy. And if it captures 8.8 electron volts of energy, it will go to the fourth level or 3 levels above ground. So what we can do is we could actually work out, for example, the amount of energy that is required to be absorbed by electrons, but also the amount of energy that is released as they fall back down, okay, which is what we're going to do right now. Okay, now you have an animation on this, which is right here. So one of the things you have to look at is This is the model of the hydrogen atom. So I'm not going to go into too much detail because that's actually part of your CPT. You got to look at this. I just want to point out a couple of things, right? So here we have white light. Okay, so if I shine white light, so here you see the middle, there's the nucleus, and you can see the electron orbiting around the nucleus, right? Now, right, that's in the ground state, and you have white light. So white light, I guess in this case, includes ultraviolet light. So you'll see the photons. So the photons are these little like billiard ball things that are just flowing through my screen. You can see that right there. And every once in a while, the electron captures energy from the photon. So right now it hasn't, but right now it did. You notice it's no longer here. Now it's all the way up here. Now, the color of light that it absorbed to make that kind of a jump must have been a photon with a lot of energy. So it wouldn't have been like a red photon. It would have been an ultraviolet photon. Now, that electron is going to come back down, right? It's not going to stay up. It's going to want to go back down to ground. And it could do it by jumping all the way back down to ground. But it doesn't necessarily need to do that. It could actually like jump from, right now it's in the 6th orbital level. It could jump from 6 to 3, for example. And then 6 to, what are we here? 6, 5, 4, 3, 2, 1. Okay, yeah, it can go from 6 to 3, and then 3 to 1. We could do that. It can go from 6 to 5, and then 5 to 1, or it can just go 6 to 1. I'll watch to see what happens here. So right now, there's my photon. Here we go. It's gonna, at some point, it's gonna jump down. So there you see. Stop. Pause. Okay. It jumped from here to here, and it released I think it was a red photon that it oh, yep, no, infrared. There's a little dot here that's saying that the photon that was released was infrared radiation, which means it's not visible light. Okay, it's longer wavelength than red light, so we can't see it. This is just simply heat then, okay? Now, the electron is in the 4th level. It's not quite at ground, so let's see what happens next. Now it's in the 2nd level. So you'll notice that it's released this blue photon, which is more energy, but it's not quite at the ground state yet. So it looks like it's probably going to release another photon. And there it goes. It went to ground and it released this photon here. And I know it released that photon because you see the trajectory is different. So in this case, the electron jumped from the 1st level all the way to the 6th. And as it fell, it released 3 different photons. And that's not always the case. I mean, let's see what happens here. Oh, did the same thing. Jumped to the 6th level. Now it jumped down to the 3rd. And then back to the 1st. Oh, seems in this case it's going back to the 6th every time. This one went down to the 3rd. And that went down to the 1st. Let's do one more. Okay, so there's an example. See how it just jumped to the 2nd level? It didn't go to the 6th level? Okay, so it obviously is going to depend on how much energy is being absorbed, right? Okay, so let's do the calculations. So what we could say is the amount of energy will be the change. So think of this as, this is the change in energy. So this is the difference between the 2 levels, okay? Where EI is the higher level and EF is the lower level. So for example, in this case, if the electron jumps from the ground to this level, the change in energy would be 4.9 electron volts. If it jumps from, for example, this level to this level, the difference would be 3.9 electron volts. Okay, so it's the difference between the levels. That's your change in energy. And the energy of the photon has to provide the energy to make that electron jump. Okay. We could say then, we could rearrange and say that the wavelength is a function of hc over the change in energy. Now, why is that the case? Because remember, E equals HF. So E equals HC over lambda. So you could see how if we rearrange, we can get lambda is HC over E, change in energy. So let's take a look at an example. Imagine that we're looking at mercury. So we have the amount of energy required to jump up the levels. And we'll look at just one case, okay? We'll look at this one. Now, if it's 3 electron volts of energy, assuming the electron is at ground state, then nothing's going to happen. The electron will not jump up. Now, what happens? The photon will pass through. That obviously will cause oscillations in the atoms and electrons, but it won't get absorbed. Remember, this is the reason why light is transparent, because the amount of energy required to get the electrons to jump is just too much for visible light. Doesn't have enough energy. So at 3 electron volts, assuming the electrons at ground state, nothing happens. At 5 electron volts, we could jump up to first level above ground. With 7 electron volts, we can get to the second level. So let's look at that one, okay? We're going to look at the scenario where it's hit with a photon that provides 7 electron volts of energy. Now, if it does this, then there's there's 3 possibilities actually. Well, not 3 possibilities, sorry. There's 2 possibilities, but with 3 types of photons that come out. So the first possibility is the electron jumps right back down. Okay, so that's one scenario. So let's take a look at that one. The scenario is, now here's an interesting thing, I was looking into this because I was thinking to myself, well, hold on a second. If the photon has 7 electron volts and the electron absorbs it, so what happens when an electron absorbs a photon? The photon actually gets destroyed, disappears. You actually see that in the animation. The photon just disappears. And then it gets, photons get recreated when the electron falls back. But here's the question, and you could look into this and tell me what you find out. I did a little bit of digging, so I think I know the answer, but I want to see what you come up with. What happens to the missing or the difference in energy? So like, for example, you need 6.7 electron volts to make the jump. But if I have a photon with 7 electron volts, there's a difference of 0.3 electron volts of energy, right? What happens to it? Because if I, think of the law of conservation of energy, this is energy. It can't just disappear. It's got to go somewhere, right? So what happens to it? So if you want to look into that, and we can talk about it, we can talk about that next time, okay? So let's assume that we ignore that little issue and the electron jumps to the 3rd level, the 2nd level above ground. And in one scenario, it just falls right back to ground, okay? Which means the amount of energy that will be released is the same as the amount of energy that gets absorbed, which is 6.7 electron volts, okay? So in that case, the wavelength of light that comes out would be, we know it's hc over delta E. So that would be 6.67 times 10 to the minus 34 times the speed of light, okay, over change in energy. But it has to be in joules, okay? Because remember, Planck's constant is joules seconds. All right, so this has to be in joules. So we got to convert electron volts to joules, which if you remember, that would be 1.6 times 10 to the negative 19 is the amount of joules in 1 electron volt. So joules per electron volt times the number of electron volts, which is, in this case, 6.7. So that will leave you with joules, okay? So that is then going to be, and then the joules are going to cancel out. So you'd be left with a unit, because this is meters per second, right? So then seconds cancel out, joules cancel out, you'd be left with meters. I guess should show you the units here. Okay, so then that would be that would give you a wavelength of approximately 1.9 times 10 to the minus 7 meters. Okay, so what color would that be? So that's a pretty big jump. What did I say was 1.9, so almost 2 times 10 to the minus 7. So it looks like, so here's blue light is about 4 times 10 to the minus 7. So this is definitely going to be UV light. So you won't be seeing this. It'll be ultraviolet light. That's one scenario. In the second scenario, the electron might do, when it falls, not just fall directly to the ground state. So maybe, for example, it will go to this level and then to this level, right? So in that case, so we'll call that maybe scenario 1. In scenario 2, it's going to go from the third level to the second level, which the difference there is, we said, so from 6.7 to 4.9, that is 1.8 electron volts. So if we do the calculation, everything's going to be the same except for the fact that it's 1.8 electron volts. Let's see how we do the units out. So 1.6 times 10 to the minus 19 times 1.8. Let me just double check. Yeah, 1.8 electron volts. So the difference between 4.7 and 6.7 is 1.8 electron volts. That will give you a wavelength of about 5.7 times 10 to the minus 7. So we said this is UV light. Then 5.7 you could see is green light. So it would be a green photon that gets emitted. And then obviously the electron then would fall to the ground state from the second level. So that would be 6.67 times 10 to the minus 34 times the speed of light over 1.6 times 10 to the minus 19 joules per electron volt. And going from ground to this is 4.9 volts, electron volts. So going from that back down to ground would be 4.9 electron volts. That would give you an associated wavelength of about 2.5 times 10 to the minus 7 meters. So sorry, this was green. So if I look at 2.5, it looks like it's beyond blue or purple, whatever color it is. So this would also be UV. But obviously, this would be UV with a higher frequency or shorter wavelength, and this would be UV with a lower frequency or longer wavelength. Okay. Any questions? So maybe what we'll do is this. Maybe I'll leave this question as review for the next time we meet. because in terms of what's left, I'm just going to go over this and talk about basically the same thing, absorption and emission, but with the hydrogen atom as a model. This is going to be a continuation of what we're doing. Okay, so why don't we stop there, and then I'll stop recording and take any questions.